We can. Yeah, excellent. Thanks very much indeed. Well, yeah, Laurence, thanks very much for the very kind invitation. Great to be here. And what I thought I would do is just sort of some ways a big picture view, an overview of physicochemical properties of drugs and optimization trends. Those are going to be the two main themes I'm going to be talking about, looking at how oral drugs properties have progressed over time, really asking the question, what changes, what does not, and a little bit of a deeper look at that. So there's been quite a lot published on that in the literature. This is a slightly deeper look on an updated database. And then have a look at optimization trends about, again, asking the same questions, what changes, what doesn't, as people start with hits and leads and take them through in successful optimizations. I'm going to sort of share with you a work in progress, really. I've been collecting this information to try to build up a picture of how different strategies affect optimization in a bit more detail. And I'll share where I've got to with that. And it is a work in progress, so bear that in mind when I get to it. Inevitably, I have to use calculated properties on this kind of work. And of course, measurements are needed in projects, and there's going to be a heavy emphasis from people later on measurement, which is terrific, and I'm really looking forward to that. So let's start with a bit of a polemic here about drug likeness and chemical space. These terms are bandied around really all the time, and I'm definitely coming to the view, and I know many people are, that these are not terribly helpful terms. Approved drugs, a few thousand of them. They're still mainly small molecules, but as we know, increasing number of biologicals and very interesting modalities, antisense, oligonucleotides, siRNA, antibodies, antibody drug conjugates, even cells. So, defining a drug is incredibly difficult on that basis. If we compare the number of drugs with published molecules and chemical abstracts, I guess these are numbers you might have seen before, but 10 to the 5 higher. And then the number of virtual molecules that one can see, one of which is quite a very interesting study. This is from Raymond's group of a few years ago, where they calculated the number of molecules that are available with 17 or fewer non-hydrogen atoms. And that's an approachable number. These days, 170 billion can almost be screened virtually, beginning to get there with those methods. So that database, I'm sure, contains undiscovered drugs, for certain. So that's quite interesting. Then moving on to the real virtual space, how many molecules you can make. Well, here's just an estimate of the building block and 2 substituents from Peter Ertl. And this is about 10 to the 20, 10 to the 24. That's probably the real world number of available molecules. And of course, there's the predicted number of 10 to the 60, which is banded around a lot, which I'm sure contains a lot of molecules that can never be synthesized. At one point, and I think it's probably going to, I hope this comes through in all of the lectures today and tomorrow, is the rule of 5. Now, I think everyone will be aware of the rule of 5. Chris Lipinski's, seminal piece of work, actually, which really pointed more than to drugs, it pointed to practice in medicinal chemistry. And at the time, Pfizer chemists were not making very soluble compounds, they're making potent ones, and they weren't soluble and they weren't permeable, and that's what brought about this rule. It is not a drug like rule. It's really important to say that. All the time people talk about this as a drug-like rule, it isn't. And a number of reasons are given below. So rule of 5 properties are not different. You look at drugs, you look at active compounds in the literature or non-drug databases, they are not different, they have the same distribution. So drugs reflect the background of compounds they come from, the background of literature and knowledge they come from. Further, oral drug properties have been transformed over time. I was talking about that. And thirdly, drug properties, they're very dependent on the target and target pursued, very different. And beyond rule of 5, I know it's been a feature of this meeting last time. These are actually turning out to be frequently bioavailable, and I'll briefly at the end of the talk discuss the AbbVie metric there and the AbbVie data. So quite a high number of bioavailable compounds can be found in this space. And lastly, transporter substrates was specifically excluded from the rule of 5 to exclude natural products, really. But actually, the transporter phenomenon may, in fact, be very common. I'm sure we'll be touching on that as we go through. So there's many reasons not to consider the rule of 5 as a drug-like rule. Please don't do so. It's a very, very crude metric. One other thing to mention right up front, and I hope folks are aware of this one, is that key molecular properties are correlated. Now, lipophilicity itself, log P, is in fact a pretty complex parameter, and it's composed of, basically it gets bigger as bulk gets bigger, and it gets smaller as polarity increases. If you just do a simple plot of log P molecular weight PSA, that's on the left, well, it's actually on left and right. On the left side of the graph, you see, left side of these two graphs, you see this plot forms a plane in 3 dimensions. So there's huge swathes here of property space you just can't fill because of the nature of that correlation. The right-hand side is rotated 90 degrees, and it's perpendicular to the plane, and you can see this is a group actually of drugs with bioavailability, not bioavailability, fraction absorbed, which was published a year or 2 ago, perpendicular to the plane. You can see the spread of the data. So that's really worth bearing in mind. You cannot independently change one or other of these properties without affecting the other. That's what this amounts to. But we continue to use them where we might use, the coordinates, principal component coordinates of this plane, which Dick Kramer many years ago described as the B and C coordinates in this really super piece of work from 40 years ago. But we don't, because we don't understand them really, and we can't really manipulate them. So we continue to use these properties, but it's really worth bearing this in mind all the time when you're thinking about molecular properties in drug design. So let's talk about what I was going to get to, the progression of properties in time in drugs. And what we see very clearly, what we've got here, and this is a large database of 2,000 drugs, and we're going from pre-1950 by decades up to the 2010s, okay? That's what we show in all of these. So it's 10-year periods, and this is the molecular weight, and here you've got a box plot showing the change in molecular weight. Here's the box plot definitions. For those of you who are not so familiar with that, the central box shows the gap between the first and third quartile, the middle 50% with means and medians and outliers and minimum and maximum values as well on this. So for all drugs, the 90% value is 528, the median is 335, and you can see currently, or the most recent drugs, are actually pretty close to the overall 90%. So inevitably from this, you can see this substantial increase, which doesn't seem to be slowing down. This increase in molecular weight just seems to be carrying on. By contrast, the change in lipophilicity is almost flat. It's really keeping almost constant, just a little bit of an increase from the 90s onwards. Hydrogen bond acceptors track the molecular weight, and hydrogen bond donors are really very similar to the log P, hardly any change. You're seeing a bit of an increase post-1990 in this. So you can interpret this saying, well, the polar properties have to keep relatively constant with donors and log P, and it's done predominantly by increasing the number of acceptors as molecular weight goes up. So that balance stays the same. And I think that balance is just worth reiterating. This is relative polar surface area, the ratio between polar and non-polar surface area in a molecule, and that is about constant over time. But also, as molecular weight increases, the allowable range of this property is becoming limited. That's in part due to the correlations we talked about. It's in part due to the need to control lipophilicity as molecules get bigger. So here's the plot of relative PSA, again through the same time periods, the 90% value, the 90th percentile and 10th percentile narrowing over time. And that's directly related to the molecular weight change over time. So shows the importance of balancing polar, non-polar metrics. And actually, I think relative PSA is underused as a property. It could be used more as an option instead of using lipophilicity. And actually, it's probably a simpler metric to calculate as well. Iron class distribution, just show this because iron class is critical in determining the DMPK properties, the pKa's of molecules. And over time, well, it stayed remarkably constant, with bases and neutrals the highest, followed by acids around 15%, zwitterions about 5%. But that slight change in lipophilicity that we're seeing is clearly a component of that is due to newer acids and newer zwitterions becoming more lipophilic, according to the X log P3 metric. Of course, the log Ds will be pretty low because they're heavily ionized, but the log Ps are actually going up, and it is a contributor to this increase. It's just beginning to happen from the 90s onwards. So acid and zwitterionic drugs are becoming more lipophilic. That's contributing to this increase. There's a couple of examples of drugs which are anionic. Here's an acid, lexocaftor, it's an acyl sulfonamide, but here's a zwitterion, siponimod. Both are pretty lipophilic and come from the most recent period, the 2010s onwards. Let's look at aromatic properties. I'm going to talk a little bit about this, and I know Rob later will be discussing aromatic properties quite a bit as well. But you know, look at the progression of aromatic properties, and we'd see, I mean, there's something quite dramatic going on here. We can see that a number of molecules which are carboaromatic, that is, they only contain benzene rings when they have an aromatic, those are dropping over time dramatically. Whereas the number of molecules that contain both phenyl rings as well as heteroaromatic rings are increasing markedly over time. And that can be accounted for again by the change, or the lack of change in lipophilicity. With increased molecular weight, more aromatics are being included in drugs, but they have to be heteroaromatic to get the log P down. That explains, and we can see a tremendous, I mean, 80, 90% now, 80% plus actually of most recent drugs are mixed heterocarboaromatic compounds. Interestingly, aliphatics, hardly used at all, you know, hardly used at all, and pure heteroaromatics that don't contain a carboaromatic or a phenyl ring are hardly there at all. These possibly are property types that could be addressed and increased in future. I don't see why not. So we can look at the aromatic ring count and the nitrogen atom counts, aromatic nitrogen atom counts. This is driving the increased number of heterocycles, aromatic nitrogens. And so those are increasing over time, as well as the ring counts, whereas the carboaromatics are staying quite level. And again, we can see this post-1990 increase in these properties, particularly the heteroaromatic nature. The carboaromatic, relatively stable over time. And that tunes in very well with earlier work from GSK folks, which talked about the developability aspects, which was mainly ADMET characteristics of drugs, where you know, the carboaromatic drugs fared less well than the heteroaromatics. There's been a lot of discussion and a lot of high-profile talk about the fraction of sp3 carbons in a molecule. Just want to point out that this is really, when we talk about FsP3, it's the same thing as talking about the fraction of aromatic atoms. So here's the fraction sp3, carbon sp3 is divided by total number of carbons. And here I've got a fraction aromatic, all aromatic atoms divided by the number of heavy atoms. And you can see there's just an inverse correlation for these two in drug sets, which has been noted in the past in these papers. And when we look at the progression of these properties over time, they are relatively constant, but we're seeing with the increased aromaticity in recent drugs, you know, an increase in the fraction aromatic and a decrease in the fraction of sp3 atoms. So, which you would expect to see. So drugs are actually getting more aromatic and not more not more sp3-like over time. Let me just dive into some interesting newer data here. This is now looking at natural product likeness in drugs. On the left here, you see the natural product class probability. This is using an algorithm called Natural Product Scout, which is very easy to use. It's available. You can use it online and put the drug data set through it. And we've got the time period again from the 50s to the current. It's very clear what's happening, isn't it? The natural product likeness of molecules is, you know, just collapsing over time. It's getting very, very much less. By contrast, that doesn't mean that natural product fragments are not being used. And this is a piece of data we've recently put together in collaboration with Herbert Waldman's group, and Herbert showed this, this graph or a similar one to it recently at the EFMC meeting in October, whereas over time we're seeing the number of pseudo-natural products, which are combinations of natural product fragments in unnatural combinations. This is what this amounts to. And here's an example of an unnaturally combined. This is not available biogenetically, this molecule, whereas the two fragments are. So the combinations of these pseudo-natural products really lead to these pseudo-natural products. And you see this dramatic increase over time, which I think is very interesting. This is being followed up now. We're in the midst of looking in detail at this. And lastly on the right, and I think it ties in with this, the novel scaffolds. This is from published data a couple of years ago. If you look at the novel frameworks that are appearing over time, and a framework is defined as just the ring topology. There's a drug and its framework. So the number of novel frameworks which haven't been made before is also escalating through that time period. So you see post-1990, watershed time around 1990, we're seeing these massive changes actually in the structures that are used in drug-like molecules, so-called drugs. So that's the end of the, I'll summarize that in a minute. That's the drug piece. I just want to move on to sort of beginning to look at optimization. This is ligand efficiency metrics. Folks are probably pretty familiar with these by now. This essentially is ways of measuring the bang for your buck, how much property you're using to get your affinity. And we've got the ligand efficiency, which is the first one of these that came along, which is the potency divided by the heavy atom count, with a multiplier here that gives you basically a kilocalories per mole per heavy atom. It's an energy unit. So it's the average binding energy per heavy atom in the molecule. Now, this has had quite a bit of criticism, it's fair to say, and it probably is, the criticism in the most is pretty fair, actually. It's kind of unreasonable to treat all atoms similarly when some of them don't bind. It has odd characteristics, like as you increase the size, it reduces the maximum LE that is available. It doesn't have a firm thermodynamic basis, that's very clear. And it increases and decreases about equally in optimizations. I'll show you that in a minute, because potency tends to go up and size tends to go up. However, it is useful for looking at hit selection, and fragment-based drug discovery folks really like this metric. And one thing I find very useful is to assess changes in optimization. So you need to be aware that when you add bulk to the molecule, you need to get an affinity increase. So adding a phenyl ring, you're going to need about 2 log units of potency even to keep equal on LE. Now it's this kind of information that's useful in drug design and analysis of data. Absolute values are not important, and it's the change in optimization that's useful here. Lipophilic efficiency, on the hand, which is just a split between potency and log P or log B, does have a plausible thermodynamic basis. There's a theoretical link to specificity, because it's like a specific versus a non-specific event that you're looking at here. As the drug can bind to octanol or bind to target, so there is a link to specificity. And this mostly increases in optimization, as you'll see later. Potency goes up and log P stays about the same. The downside of this is you can get a high lipophilic efficiency by simply lowering log P, and that's not a good place to be. It's going to affect your permeability. You've got to have an optimal log P, and you need experimental data, obviously, to do this in the best way in your project. Getting high values is good. I think there is general agreement that high values above 5 are the place to be. Again, looking at change in optimization is a useful measure. And I think the community are recognizing this as an important metric in optimization. But I think actually both are probably important. And let me show you this slide. This is from a publication we put out last year. And this compares how drugs compare with, this compares drugs with molecules that are published that work on their same target of the drug. So this plot, here's the definitions of these two properties again. This plot shows the difference in both LE and LLE between the drugs and the median value of compounds which act at the drug's target, where there are more than 100 compounds. All right, so We know drug works at a particular target where there are more than 100 compounds that work at that target. Simply take the median value of all of those other compounds, and that's the median other compound that represents the target. And it's the difference between those that is on this graph. So you've got the difference in LE between drug and the target compound, and the difference in LLE between the drug and the target median compound. And the red lines show where the drug will have the same value as the target median, LE and LLE. And you can see from this that, in fact, when you work out the numbers, 96% of drugs have greater values of both of these parameters against, or both or one of these parameters, should I say, against the target median. And further, as we showed in this paper, if you use the rule of 5 properties, they just don't differentiate the more recent drugs at all in this analysis. Just a few examples of some recently invented drugs, which have been quite challenging. A couple of these are peptidic GPCRs, CGRP, and here's one example, rimegepant, here's Relugolix, a gonadotropin receptor hormone antagonist. Large numbers of comparators that we use for the analysis. This is a JAK3 antagonist, a kinase, which is the most ligand efficient, but still these quite challenging molecules are more ligand efficient than other compounds that work on their target. So if you want a drug-like rule, I'm not proposing this as a drug-like rule, but throwing potency into the mix, along with size and lipophilicity, really does begin to distinguish, at least according to published compounds, drugs from other molecules. Okay, what happens to, I'll move on to the optimization piece. Laurence, have I got time? I'm just realizing I'm going on a bit. I'll try to speed through this. I hope I'm okay.
No, you're all good. Take your time.
I'm okay, good, thanks. You can always shut me up when you want to, you know.
Okay.
Okay, but what happens to physical-chemical properties during optimization? Well, you know, the idea that came up many years ago, and this is a paper I'm very proud of actually, we put out many years ago from AstraZeneca, talked about the lead-like hypothesis. Basically, in optimization, some properties increase. So keeping molecular weight and log P low and potency, this was the key thing of this paper, you don't have to worry about potency, that can be low as well. If molecular weight and log P are low, that allows multi-parameter optimization by allowing growth into what might be considered drug-like space, which tunes into the normal practices that chemists adopt when optimizing molecules. Sorry about this table, I threw all this lot together, but this is a summary of what's been published up to now with successful optimization, start to finish pairs, going from historical, a couple of historical papers which really followed up this one from Mike Hanna and from Tudor Aprea, who is a co-author here, looking at historical lead and drugs from various sets in the literature. Then we had a specific lead and drug set, came along later. Then there was a set of molecules that look at drug to drug, basically. And then a recent study here from Dean Brown, which is a nice one, looking at hit and candidate. So the basic message you can see is the molecular weight does indeed go up in all of these, except when you move from drug to drug. In fact, the drug to drug data, nothing changes. H-bond donors, nothing changes. Molecular weight goes up, H-bond acceptors on the whole go up, and log P sometimes up in these early studies, but in these more recent ones, very little change in lipophilicity. So lipophilicity looks to be something that's better controlled later on. Notice the starting points and finish points in terms of size of molecules from history up to the current time, both are increasing in these data. So what I want to do, just show you what I've done to sort of back up some of those observations, and particularly to build on Dean Brown's nice work here. It was only 63 compounds, and it really needs a larger set to examine the strategies used, which they discuss in this paper, and how those might affect optimization. So this is a work in progress. It's up to over 300 start to candidate pairs. These are actual candidates, as described in the literature, that are going to the clinic. They're mostly from JMed Chem. They're mostly oral candidates, and they're mostly antagonists. That's how it turns out. It's pretty mainstream stuff. And of course, try as you can to get things up to date. and I've collected the patent data. The average age between the publication, the average age of these optimizations is 7 years at least. Some of them much older, some more recent. So this is about as recent as you can get. And it's worth noting in terms of kind of the new modalities, the PROTACs and peptides and so forth, which are beginning to be talked about a lot. There's relatively few of these. In fact, there aren't any PROTACs described in JMed Chem as candidates, although numerous papers discussing PROTACs. So if we look at the breakdown of where the molecules come from, where the drug candidates come from, this is the analysis we're going to be looking at quite quickly now. We've got really about an equal emphasis on knowledge-based and screening-based methods. So you've got drugs themselves, actually are still starting points, 13%. Known compounds in the literature, 28%. Taking known compounds and devising new ones based on pharmacophore hypothesis start points, a significant component. Focus screens, which include virtual screens, ligand-based screens, structure-based approaches, quite significant. Small amount of fragments, and then a large number of dominated by high throughput screens, random screening. So that's what it looks like. You're sort of getting increased knowledge as you move around anti-clockwise here. So just look at the random screening hits to start with. And this shows how potency changes. Potency always goes up in these optimizations, of course. So how does potency change as a function of molecular weight, and potency as a function of log P? And I think you can see by eyeballing that, got the numbers below, you can see by eyeballing it, that as potency goes up, there's pretty much a tendency to increase molecular weight at the same time. But as potency goes up, log P, it can stay the same, go up or go down. In fact, in this set, it goes down a little, it goes down by about half a log unit. So that shows the control of log P coming in. So you can ask, do these screening hits fit to the rather old Teague criteria from the lead-like paper that we talked about a moment ago? And they don't. Only about 18% are less than 350, less than 3 on a log P basis. Whereas more of them, of course, 40% actually break both of these. I'll come back to this towards the end. Do we need a new definition, or is there an issue here? We'll discuss that. But each case is unique, as you can see. So when you're looking at these kinds of data, you have to remember the spread of the data. The fact that each case is unique, but you can pick out broad trends. And it looks like low molecular weight hit selection is happening. We'll go 376 is the mean, going up to 456, and lipophilicity control is being exercised. So this just shows the molecular weight again for all the different strategies now. On the right is the random screen you've just seen. And the message from this is basically they're starting in different places, but the optimization simply takes them to a very similar space. So the red bars are the changes as you move from start to finish. The green bars are the finished candidates, the blue bars are the starting points. That's what these are, box plots again. So you can emphasize this fact of change in molecular weight. You can look at the change in molecular weight and go as you move from the candidate through to the starting point through to the candidate. So that's a change in molecular weight. You can start molecular weight. Lower molecular weights increase more, higher molecular weights increase less. And this is a very, very generic thing that you see. So lower values increase the most. And you see this, I can assure you, with pretty well every property you look at. Doesn't matter what it is, you see this. This kind of graph between the change and the start is nearly always a negative slope. You can see here for drugs, it's almost flat because they hardly change. So this is a kind of convergence to a drug norm that is happening. The start points are different, but the drugs all look similar. And it's the drug properties that are the driving force. This is akin to a regression to the mean, which is a statistical phenomenon when A versus B has a slope of less than 1. And that's basically what you see here. Start versus finish has a slope of less than 1. So I'll just whisk through the rest in the interest of time here. If we look at log P, we see that log P is hardly changed except for fragments. And there's the same convergence, if you like. to the drug-like properties we see. And all the candidates have the same log P in this particular instance. Let's just look at the overall changes in H-bond acceptors and donors. This is quite interesting. This actually replicates, the earlier data in that donors don't change much, acceptors change much more. And we can see that H-bond acceptors, 67% of cases, there's an increase. H-bond donors, mainly there's no change, and you can go up or down about equally, a small increase in H-bond donors, but not many. And as you optimize, the balance of acceptors to donors simply gets less. Donors do not increase. And there's been really quite a nice paper from Peter Kenny come out just recently, talking about H-bond donors. A lot of very thoughtful insights in there. And H-bond basicity, but not acidity, we know already lowers log P. So the H-bond acidity hardly affects log P. So to get log P down, it's going to be mainly acceptors that will do that. And acceptors are generally more polar than H-bond donors, according to arcane water measurements, as discussed by Kenny. So there's something interesting. H-bond donors have got a bad rap for being bad. You have to keep them, as you saw, they weren't changing much in drugs. And I think we know that when we block H-bond donors, we tend to get much better permeability on the whole. So there is something to that story. But in terms of the polarity of these two groups, it's certainly acceptors play the role in manipulating log P more than do donors. Look at the efficiencies. What we see is, and this is what I touched on before, is that in general, LLE increases. Look at these red bars all going above the no change. If there's no change, everything would be on the 0 line. Drugs and known compounds don't change much, but all the screening examples, there's a nice increase. And all the drugs end in the same place. The mean is 5.3. And with LE, this is typically what you see. LE is just flat lines right across the board. Start and finish are about the same, and there's no change. And that sounds like it may not be important, but it is important, because as you increase molecular weight, you really have to increase potency in a successful optimization. And in fact, as molecular weight gets bigger, the maximum allowable LE gets less. So in fact, these, although it doesn't show in the metric used, there is actually improved efficiency through size as molecules get bigger and the LE stays the same. So I had some examples. I think in the interest of time, I'm going to flick past them. I'll move on to aromatic counts. Realize I am using time, but this is aromatic ring counts. And the bottom line here is that between start and finish, really there's no change at all, apart from fragments. So what we see is the start equals the finish in every case. In other words, the starting molecules come with a full aromatic ring complement, which cannot be increased further. I think it's an important observation. What does change is the type of aromatic, and this is consistent with what we saw before. The carboaromatic rings, in other words, phenar rings, tend to reduce. Heteroaromatic rings go up, and that is significant in many cases here. In many of these strategies, that is a significant change. Drug starting points, like we see with nearly everything else, start with a drug, it's pretty well all the optimization in terms of properties is built in already. So this is the change, as we would expect to see to control lipophilicity, more heteroaromatics, less carboaromatics. But point out really, in most cases, look at a number of start candidate pairs. In most cases, no change in these, because you're already at full complement. Heteroaromatic rings go up a little, and carboaromatic rings go down. So we're already at candidate levels, and you can ask questions here about whether we're choosing the right hits. Are they too aromatic to begin with? I know there's a lot of discussion about that in the literature too. And in terms of the CSP3 and fraction aromatic atoms, we see the predicted things. FSP3 goes up, the fraction aromatic goes down. You'd expect to see that. And it's interesting that the random screening compounds, because they're lower molecular weight and have the same number of aromatic rings in, as the higher molecular weight starting points, you tend to see these have a lower fraction sp3 and a higher fraction aromatic than some of the other strategies. So and so do the fragments as well, actually. So these screens, which just start off with aromatic rich compounds for their size, are actually producing aromatic rich compounds compared to some of the other strategies at the end of the day. And this now compares, sorry to show you, the burden you with a lot of data here, a lot of graphs. This looks at overall aromatic atom count and the CSP3 atom count. So here's the aromatic atom count, hardly changing at all. In fact, mostly they stay the same, go up or down about equally, whereas CSP3 atoms go up. And we can look over here and see the number of aromatic atoms and the number of aromatic nitrogen atoms. Aromatic nitrogen atoms increasing, non-aromatic nitrogen atoms, in other words, mainly carbon, sulfur, and oxygen, predominantly carbon, don't change at all. Look at the CSP3 atoms. What's interesting here is that does increase on average overall through its process, but all this data together, we've got a difference of about an increase of about 3 sp3 atoms. And if you look at all carbon atoms, it's 3.4. So the increase in tetrahedral carbon atoms accounts for nearly all the increase in carbon atoms in optimization. So I think it's clear that aromatic components are already very high in starting points, and that adding aromatic nitrogens helps control lipophilicity. CSP3 gives most of the carbon increase. Carboaromaticity is very controlled, CSP3 is not. So the hypothesis is, can you untangle this? Well, aromatic control is required, and Rob will talk about this later when he talks about the property forecast index, which combines lipophilicity and aromatic rings. Whereas I would suggest that tetrahedral carbon atoms, that's permissive lipophilicity. It's allowable lipophilicity. Of course, it's useful to use that, whereas aromatic lipophilicity is less useful and comes with more issues, many of which can be shown experimentally. Right. I'll finish in a minute, Laurent. I'm going to finish now. Let's just look at the overall changes in the number of atoms. Now, we know that small changes to structures can make a very significant difference in optimization. Adding in a methyl group or a fluorine or a hydroxyl, putting in an aromatic nitrogen atom, these are 4 things that do make significant differences. And actually all of them increase in optimization. But in most of these cases, no change is pretty dominant. Here we've got stereocenters, the last 2 interesting points, allied, I think, to the increase in tetrahedral carbon. We've seen an increase in stereocenters. This is very marked versus about 5% only of these optimizations reduce stereocenters, 41% increase, 54% don't change. And non-aromatic rings is comparable, actually, which use sp3 centers as well. So these are trends behind those optimizations, showing the use, if you like, of 3-dimensionality sp3 atoms in optimization, and as you've seen already, the lack of change in aromatic atoms. I'll skip the example. I was going to talk a little bit about beyond rule of 5. I just want to say, I'm not going to say any more about this. I know you've discussed this before. This is the world record compound, as far as I'm aware, that's made it as a drug. It's Bibrentasvir. It's AbbVie's NS5A inhibitor for hepatitis C virus. It breaks all the rules, but it has really rather a good lipophilic efficiency. It is bioavailable. You need to take it with food. It's probably not a very soluble compound. And I think, as we've seen, many of the insights that are coming along here in this area are to do with conformation, chameleonicity, hydrophobic collapse, intramolecular hydrogen bonds, exposed polarity, all of which play a role. And we've got the EPSA measurements, I think we'll be hearing about later, and delta log P to look at polarity. These are dynamic polarity measures. I think these are really important for RO5 compliant molecules as well in more regular space. There's no reason why they shouldn't be. And there's already some nice literature on this from the Merck folks talking about EPSA in different environments. What I will, whoops. Oop.
Yeah, I'm not sure.
Sorry.
I'm not sure actually.
I'm probably going to.
Activity. Of course,
I'm probably going to
the defense
stop.
line binding. Quite often they don't translate into functional.
Just summarize, folks. I'll just summarize quickly.
Electrophysiology, you know. So.
Hello, but I can hear someone else speaking. Never mind. So properties are the most important. You know, those properties which change least over time and least prone to changes in optimization are the most important to control. And you've seen what they are. It's lipophilicity, polar, non-polar balance, donors, and this aromatic component. And it's pretty much this. The good news is it's the same in optimizations. And it's a short list of things. These are the most important things to control, it looks like. We can add to this the LE and LLE of optimized drugs appears to be important. And we've seen this post-1990 change, which can be tied back to, I believe, the introduction of screens for human targets and library synthesis, which started at those days, which led to accelerated in vitro potency optimization. That's what's led to these changes in properties. About optimization, the hit profile is not a major driver. You just get convergence to a candidate profile. I think we can ask questions over whether we're using the right hits. Are they too aromatic, too lipophilic, not sufficiently lead-like? That's a good point for discussion, I think. And one which I think has caught on with a move towards getting away from aromatics, really, and starting points. Things that increase are things you can use. And these things you can use, this is a toolbox you can use to optimize your molecules to increase, and they increase in both drugs and in optimizations. And what's particularly interesting, and I think where this is going to go now, is to look at this from more of a structural net point of view. Look at frameworks, and especially this natural product scaffold concept, which I mentioned earlier, which I think is fascinating. So I'll stop at that point. Sorry to have gone on a lot, but thank folks. Many folks are involved. This is the folks at EMBL who did a lot of the work with Kemble that I showed you on the ligand deficiency, Patricia and others. Thanks to the folks in Dortmund, Axel and Herbert, for the natural product calculations. And a special thanks really to Andy and Rob, who've been sort of longtime colleagues and friends in discussion about physicochemical properties and have influenced me a lot, as have many others at AstraZeneca and GSK. So just finally, thank you, Laurence, for the invitation, and to point out on this very nice poster, you got it right. You got all the important things here. I didn't really need to say anything. It's already on this on the flyer. So sorry to go on a bit, and thanks for listening.
Thank you so much, Paul. Very, very insightful. I like the whole overview and see where we are going. I don't know if we have a lot of questions. Someone has.
I did have one come through. Here is a question. As a lot of crucial properties show no change or significant change, does it mean we have found the optimum properties where the molecules are more likely to become drugs?
Yeah, I think that's a reasonable assumption that is the case, especially for oral molecules. That was largely oral small molecule space. That's the caveat to that. I would say for molecules administered by other routes intravenously, it could well be a different story. When you look into that, though, the intravenous drugs are not hugely different to other molecules in terms of the properties, but I think that's a reasonable thing to say, and that balance of properties which are pretty constant in drugs and don't change much in optimization, they're the result, they're the properties you have to control to get exposure of your drug to the target of biological action. I think, in other words, you know, getting, largely speaking, I would say the permeability and the ADMET properties in the right place and balancing those in the right place. So that's the conclusion you would reach, yeah.